The video lecture for section 6.1. This is a standard normal distribution. This is for STA 2023, and my name is Jorge Gavillan. So the key concept here, we're going to present the standard normal distribution, which is a specific normal distribution having the following three properties. It is bell-shaped. Mu is equal to 0, so the standard normal distribution has a mean that's equal to 0. And sigma is equal to 1, which means that the standard normal distribution has a standard deviation is equal to 1. In this section, we're going to develop the skill to find areas or probabilities or relative frequencies that correspond to various regions under the graph of a standard normal distribution. In addition, we're going to find z-scores that correspond to areas under the graph. So, if a continuous random variable has a distribution with a graph that is symmetric and bell-shaped, we say that it has a normal distribution. Here's the equation of that. We don't have to worry about that in this course, but that is the equation for a normal distribution. Now, curve is bell-shaped and it is symmetric. Mu is in the middle of the bell curve, and that's the values in the horizontal axis. So some properties. The next thing we're going to talk about before we get into the standard normal distribution is the uniform distribution. And a uniform distribution has the following properties. The area under the graph is a continuous probability that's equal to 1. There is a correspondence between area and probability, so the probabilities can be found by identifying the corresponding areas in the graph using the formula that the area is equal to height times width. Uniform distribution is a continuous random variable. It has a uniform distribution if the values are spread evenly over a range of possibilities. And the graph of a uniform distribution results in a rectangular shape. So, density curve. The graph of any continuous probability distribution is called a density curve. And any density curve must satisfy the requirement that the total area under the curve is exactly 1. Because the total area under any density curve is equal to 1, there is a relationship between area and probability. So, here's an example for uniform distribution. During certain time periods at JFK Airport in New York City, passengers arriving at the security checkpoint have waiting times that are uniformly distributed between 0 minutes and 5 minutes. And so, since it's a uniform distribution, all the different possible waiting times are equally likely. So you can see here that this would be a uniform distribution. Now, waiting times can have any value between 0 and 5. Since it's continuous, someone can have a waiting time of 1.2, 3, 4, 5, 6, 7 minutes. Now, by assigning the probability of 0.2 to the height of the vertical line in the figure, the enclosed area is exactly 1. In general, we want to make the height of the vertical line in a uniform distribution equal to 1 divided over the range. Now, given that the uniform distribution illustrated in this figure, find the probability that a randomly selected passenger has a waiting time of at least 2 minutes. So from the previous lecture, at least means 2 minutes, 3 minutes, 4 minutes, or 5 minutes. So the shaded area in the next slide represents the waiting time for at least 2 minutes. Because the total area under the density curve is equal to 1, there is a correspondence between the area and probability. So we can easily find the desired probability by using areas. So the probability of wait time of at least 2 minutes is equal to the height times the width of the shaded area in the figure, which is 0.2 times 3, which is 0.6. So the probability of randomly selecting a passenger with a waiting time of at least 2 minutes is about 0.6. So now we're going to talk about the standard normal distribution. The standard normal distribution is a normal distribution with the parameters of mu is equal to 0 and sigma is equal to 1. And the total area under this density curve is equal to 1. So we can find areas or probabilities of different regions under a normal model using technology or a table. We're going to use technology in this course. So we're not going to worry about using the tables. Now, one thing about it is that when working with a graph, avoid confusion between z-scores and areas. Z-score is the distance along the horizontal scale of a normal distribution, corresponding to a number of standard deviations above or below the mean. The area is the entire region under the curve. Now, the part of the z-score denoting hundreds is found across the table A2. So if we were using the table, we'd have to worry about all these things, but we're not going to be using the table. So here's an example. A bone mineral density test can be helpful in identifying the presence or likelihood of osteoporosis. The result of bone density test is commonly measured as the z-score. The population of z-scores is normally distributed with a mean of 0 and a standard deviation of 1. So these test results meet the requirement of a standard normal distribution. So the graph of a bone density test is shown in the figure. So a randomly selected adult undergoes a bone density test. Find the probability that this person has a bone density test of less than 1.27. So when we graph this in a standard normal distribution, the z-scores is always 0. Z-scores to the right are positive, to the left are negative. If someone has a z-score of 1.27, they'll be around here approximately. So then the probability that a person has a score less than 1.27 will be 0.898, or about 89.8%. And so remember, everything to the left of this line plus everything to the right will equal 1. And the way that they find these values is actually using calculus. Now, note the following are the same because of the aforementioned correspondence between the probability. So probability that the bone density test scores less than 1.27 is the shaded region in this figure. So we need to find the area to the left of 1.27 using the tables, which we're not going to be using the tables, but if you were, you would just use find the convergence of the row and the column. And let me skip this again. So how do you interpret this? The probability that a random selected person has a bone density test result below 1.27 is 0.898, shown in the shaded region. Another way to interpret this is to include that 89.8% of the people have bone density levels below 1.27. Now, using the same bone density test, find the probability that a random selected person has a result above -1, which is considered to be in the normal range of bone density readings. So here again, using this figure, we can see that above -1 would be the following. So above -1 is 1.57, and then so using the table we get 1.57. Now, since we want everything above the -1, we have to literally subtract this from 1 to get 0.8413. And the nice thing is when we use technology, you don't have to worry about doing all of these different things to find this information. So, because of the correspondence between probability and area, we conclude that the probability of randomly selecting someone with a bone density reading above -1 is about 84.1%. Now, the next one, bone density reading between -1 and -2.5. So, in the case of the subject, is in fact has a form of osteoporosis, so which is some bone loss. So, we're going to find the probability that a random selected subject has a reading between -1 and -2.5. So, if you were using the tables, we would find the area to the left of -1, the area to the left of -2, and then the area between these two is the difference between these two would be our answer, which is this region right here that's shaded. And so again, there's a relationship between probability and area, so we conclude that the probability that someone has bone density between -1 and -2 is about 15.2%. Now, there is a general rule. So the area corresponding to the region between two z-scores can be found by finding the difference between the two areas found in table A2. We're going to be using technology, so we don't have to worry about the tables. Don't try to memorize a rule or formula in this case. Just try to understand what it means when we find different areas or probabilities. So there are some notations that we're going to be using in the rest of the course. So the probability of A less than Z less than B denotes the probability of the z-scores between A and B, some values A and B. Probability that Z is greater than A denotes the probability that the z-score is greater than A. Probability that Z is less than A simply denotes the probability that z-score is less than A. So we can also find z-scores from known areas. So we draw, if we weren't using technology, we would draw a bell-shaped curve and identify the region on the curve that corresponds to a given probability. If that region is not cumulative region from the left, work instead with a known region that is cumulative region from the left. So using technology or the table, we can find the z-score if we know the probability. Now, critical value, this is going to be important because we're going to be using critical values when we get into hypotheses testing. So for a standard normal distribution, critical value is a z-score and a borderline separating those z-scores that are significantly low or significantly high. So notation, the expression z alpha denotes a z-score with an area of alpha to its right. So if we get a value, find the value of z 0.025, alpha is 0.025 in the expression, so we're going to find the value of this particular z-score. So notation is used to represent the z-score with an area of 0.025 to its right. Now, if we refer to this figure, note that the value of z is equal to 1.96 has an area of 0.025 to its right, so z 0.025 is equal to 1.96. One thing of note that some of these values are standard, like 1.96 is standard. There's also 1.65, 2.33, 2.58, and those values are going to make sense as we get into hypothesis testing. So there is some caution so be careful. But we are going to use technology to find these, so to become a little easier. But you still have to understand what it means, right? Not just finding a value. What's the significance of the value in the context of the problem that you're trying to solve, or the question you're trying to answer? And that's the end of 6.1. Thank you.